Well, it's next time, and here we go with the harder problem. It's the hammock problem, but the 5 Newton weight is held up with the spring scales at two different angles. So let's go to a free body diagram, and let's draw in our X and Y components. Remember, we're trying to find the force of the right spring scale and the force of the left spring scale. Well, that's two unknowns. So we'll need a couple of equations. Since the ring doesn't move, we can say the forces pulling to the left equal the forces pulling to the right. Well, that's these X components. The component pulling to the left would be the force of the left spring scale times cosine of 20 degrees. The component pulling to the right would be the right spring scale times cosine of 40 degrees. A moment with the calculator, and we have one equation, but with two unknowns. That tells me we need another equation. Well, let's look at the Y components. The forces going up have to equal the forces going down. The Y component for this vector would be FL times sine of 20. This Y component is FR times sine of 40. It's going in the same direction, up, so we add them. And the 5 newtons is going down, so we put that on this side. The forces up equal the forces down. Again, with the calculator, we set up this equation. Another equation with two unknowns. Well, now I have two equations and two unknowns, so we can substitute and solve for either one of them. Let's rewrite this equation and solve for FL. We just take the 0.766, divide by the 0.9397, and we have 0.8152 times FR equals FL. Now I can substitute that in on this side. I'm bringing this term and putting it into here. I write it all out, and now we can multiply through and add it up. Now I can solve for FR. Well, we have one of them. I can now plug this value back over here and calculate FL. And here we have it. We can put these values up here on the diagram and see if it really makes sense. If you took this value times the sine of 40 plus this value times the sine of 20, we can check to see if they're equal to 5. Or we could take this value times the cosine of 40 and see if it's equal to this value times the cosine of 20. This is the component method, and it requires simultaneous equations. Could you imagine doing this on a quiz? It's really going to take you a little while, but there's another way. Watch what happens when we put these vectors tip to tail. I've made the diagram just a little bit bigger for clarity. We'll start with the weight vector. That's going down. I throw in a coordinate system, and now I'm going to bring this vector down here. I measure out 40 degrees, and then I draw a line, but I really don't know how far to go with that line. But I do know that somewhere along this line, the other vector is going to have to go and finish the diagram so they can all add up to 0. I can backtrace this line until it intersects. Now I know FR is this long, and FL is that long. Let's get some angles inside this triangle. If this is 40 degrees, that's got to be 50. If this is 20 degrees, this has to be 20. FL has to go 20 degrees clockwise from the negative x. If this is 40, this angle has to be 40. So what's the angle between these two here? That's 60 degrees. If that's 60 and that's 50, this has to be 70 because they all have to add up to 180. Well, now we can use the law of sines. 5 newtons over the sine of 60. There's your 5, there's your 60. FR over the sine of 70. FR over the sine of 70. Well, if you do the math, guess what you get? The same thing. And we can do the same thing to get FL using FL over the sine of 50. And if you do the math, you're going to get the same thing. Okay, the truth is that there's less math here, but the trouble is the triangle, getting that set up with the right angles and putting these vectors tip to tail. People can screw that up. Some of them would rather do the simultaneous equation method. Me, I'd rather do this. And of course, this should support the components in the vector problem. For example, here I've drawn in all the components of FR and FL. Look at the FX. You can see that it goes to the right just as far as the FLX goes to the left. And we can see that the Y components add up to the weight of the object going down. So it's all supportive of each other. And what would happen if we drew the vectors in a different order? Let's bring FL down, followed by FR. This angle in here would be 60 degrees, this angle 70 degrees, and that angle 50 degrees. Use the law of sines, you'll still get the same answers. And of course, the last thing you could do is draw everything to scale, measure everything with a protractor, and then you can measure the lengths of these lines and convert them to forces, and the graphical solution will support the mathematical.